Hi, my name is Cheng, and I go to Green Level High School in Cary, North Carolina. So I'd like to start by sharing one of my favorite TV show characters. This is Stefan, and you think he's just a normal guy, right? Well, what if I told you he's actually 161 years old? That's because Stefan is a vampire, and vampires never age. And you're probably sitting here wondering why I'm talking about vampires, which is pretty fair. Well, unlike vampires, which never age, our endothelial cells, or blood vessel cells, they're gradually aging as we grow older. And this is known as endothelial cell aging or endothelial cell senescence, which leads to inflammation, oxidative stress, and ultimately cardiovascular diseases, which are the leading cause of death worldwide, killing 17.9 million people in the world annually. And cardiovascular diseases like atherosclerosis and hypertension are usually caused by aging and damage to blood vessels over time, meaning they all circulate one origin, which is endothelial cell senescence. And essentially how this works is when our endothelial cells become old and senescent, they lose their ability to divide and repair the blood vessels properly. And so when the blood vessel walls deteriorate, this makes them more vulnerable to plaque buildup and makes the blood flow more impaired, which increases the risk of cardiovascular diseases. Now the problem is that current treatment methods like antiplatelets and anticoagulants, they only manage the symptoms and reduce blood vessel blockage rather than addressing the root cause of endothelial cell senescence. So, what if there was a way for our endothelial cells to always stay young and defy aging, just like vampires? Well, this is where microRNAs come in place. And I became so intrigued in the emerging field of microRNAs when I read about the 2024 Nobel Prize in Physiology or Medicine, which was awarded to Victor Ambros and Gary Rudkin for their discovery on microRNAs. And essentially, microRNAs are these small, non-coding RNA molecules that regulate gene expression by binding to messenger RNA or mRNA and preventing protein translation. And ultimately, they play key roles in cellular processes like inflammation, apoptosis, and aging. So I wanted to see if certain microRNAs have the therapeutic potential to reduce senescence. And so after conducting many literature reviews, I landed on a specific microRNA, MIR 26A5P, which is known to suppress inflammation and inhibit cell apoptosis, but hasn't been tested for its effect on senescence or cardiovascular health yet. So my idea was to deliver these therapeutic microRNAs using a minimally invasive microneedle patch. And so how this would work is, so we have the patient's arm here, and a patient would apply the microneedle patch onto their arm, which is really tiny. And the microneedles will penetrate the skin in a minimally invasive and painless manner, and then release the therapeutic microRNAs. And so the microRNA's role here is to reduce endothelial cell aging. So how this would work is when the microRNAs reach the blood vessels and reach the endothelial cells, it will help rejuvenate the endothelial cells. So here would be the original damaged endothelial cell or senescent cell, and then the revived cell. And so when the endothelial cells become more healthy, this will allow the blood vessels to also become rejuvenated. So where there was once plaque buildup, it will become a healthy blood vessel and ultimately treat cardiovascular diseases effectively. And I named this innovation Vampire, which stands for Vital Anti-Aging Microneedle Patch for Induced Regeneration, because the microneedles are like the fangs of vampires, and this patch can also reverse endothelial cell aging, just like how vampires never age. So I first had to see which microRNAs decrease with age and which increase with age. And to do this, I tested the expression of different microRNAs in young exosomes and old exosomes, because exosomes are these rich carriers of microRNAs, and they're extracellular vesicles. And so the microRNAs that are more present in young exosomes can help reduce endothelial cell senescence, and the microRNAs that are more present in old exosomes can contribute to endothelial cell senescence. So after I isolated the plasma exosomes using ultracentrifugation, I characterized these exosomes using NS300 technology in Miranese kits. And I found that more beneficial microRNAs are highly expressed or upregulated in young exosomes compared to old exosomes, while senescence-related microRNAs are downregulated in young exosomes and more highly expressed in old exosomes. So knowing that young exosomes have higher expressions of beneficial microRNAs, including miR26A5P, I then tested young exosomes versus old exosomes on senescence pathways, including senescence itself, inflammation, and DNA damage. So I did some immunofluorescence staining procedures to measure the expression of 5-3BP1, the DNA damage marker, NF-kappa B, the inflammation marker, and SA-beta-gal, the senescence marker, and found that all of these markers were significantly reduced in the young exosome treated senescent cells compared to the senescent cells itself and senescent cells treated by old exosomes. And so this shows how therapeutic microRNAs are for reducing endothelial cell senescence. And I also did some flow cytometry experiments to measure the cell cycle distribution of each group, and I found that young exosomes treated cells had the longest S phase compared to the other groups. And the S phase is also the DNA synthesis phase, and this means that the young exosome treated cells had the less DNA disruption compared to the old exosome treated cells and senescent cells. And so what this means is that the DNA synthesis is more enhanced in young exosome treated cells, and this contributes to reducing endothelial cell senescence. And I also, in my literature reviews, I saw that cellular enlargement is another indicator of senescence. So I also did some imaging for the groups, and I found that just from visual observation, I saw that young exosomes significantly reduced the size of the senescent cells. And so then I thought about how I would actually deliver the microRNAs using microneedle patches, but I realized that natural microRNAs are unstable and degrade quickly. So then I sought to use miR26A, which is a mimic of miR26A5P that is chemically modified for stability and is able to survive longer under extreme conditions like under microneedle patch delivery. So then I tested the therapeutic effect of miR26A. And for this, I measured the expression of a protein called Ki67, which is an indicator of cell proliferation. And so what I saw was that the miR26A group had more Ki67 plus cells than the others, which indicates more cell proliferation and cell division ability, and most importantly, its regenerative ability. So after all those in vitro experiments, I then conducted some experiments focusing on the microneedle patch and its mechanical properties. So I first took some scanning electron microscopy images of the microneedles to measure its height to be only about 400 micrometers. And then I used a rheometer to assess the mechanical strength of the microneedles and saw that it was able to maintain structural integrity even under intense pressure. And lastly, I actually applied the microneedle patch onto fresh pork skin. And I saw that over the course of 10 minutes, the microneedles gradually dissolved, which indicates its ability to provide a sustained drug release, which means that it would provide a steady therapeutic effect over time. And so what I think makes Vampire so promising is its effectiveness and convenience, especially the minimally invasive aspect. So here I have a skin model. And this is what a typical syringe looks like the ones doctors would use to draw your blood. And this would be the size of a microneedle. So you can see the clear difference in just how painless and minimally invasive the microneedle would be. And this is the PDMS mold I used to fabricate the microneedle pouch. It's very small. And this is what the microneedle pouch actually looks like compared to my finger, which is really small and minimally invasive. And so I can definitely see Vampire as something that would seamlessly treat and prevent the progression of cardiovascular diseases. However, there's also so much room for further improvement and testing, especially in vivo trials or in vivo studies, and eventually clinical trials to validate the efficacy and safety of Vampire. And I also think that this research deeply impacted me as a person, and throughout the process, I learned that setbacks are stepping stones, and you have to be truly passionate about something to make it work. And it's okay to ask for help sometimes, because throughout the research process, I encountered many challenges, but I learned to persevere and embrace feedback and advice from my mentors. But overall, I think Vampire has so much potential to save millions of lives worldwide, and also introduce a novel therapeutic approach of combining microRNAs with microneedles. And this approach can be applied to other health issues like diabetes and cancer, and just make great contributions to the scientific field overall. And I'd like to thank my mentors, Dr. Wu Bing Bai and Dr. Tommy Karanosis, for their continuous mentorship, encouragement, and guidance, and UNC Chapel Hill for providing the resources and lab environment. And thank you so much to the Davidson Institute for reviewing my application and providing this amazing platform for me to showcase my research. Thank you for watching, and together we can save millions of lives with Vampire by reviving blood vessels, reversing time. Thank you for watching.